Okay, so let's continue for our revision of the chapter Deformation of Solids. So let's proceed. Let's start with number one. Okay, the formula of the velocity of the longitudinal wave which travel along a road um, along a road made of material Young modulus E and density rho is V equals to surd E divided by rho. Show that the formula is dimensionally correct. Okay, so first of all, let me close this. Okay, so first of all, we need to know that Young modulus is actually equals to stress over strain. Stress over strain, so it's actually equals to F over A times L naught over E. Since strain is actually equals to extension over the original length, so reciprocally this one will be moved up and this L naught will be moved up, so it's actually equals to L naught over E. So this is the formula for a Young modulus. Okay, we need to know that, so this is actually equals to MA. F is actually equals to MA, so this is A and this is L naught and this is E. So okay, in terms of SI units, okay, so this one shall be kg ms milli per second square, which is for acceleration. So this is m square for the cross-sectional area. So this L naught is actually m, and this extension is also m. So this can be cancelled, and this one is L. Okay, so this one will be 1. Okay, so the final answer we get is actually equals to m negative 1 s negative 2. So this is the SI unit for Young modulus. So let's look about rho, the density. So density is actually equals to the mass divided by volume. So the mass is actually kg and the volume is actually meter cube, which is rho. Okay, so let us see whether it is dimensionally correct. Okay, so this one shall be 1 over 2 since surd is the power of 1 over 2. Okay, so let's just substitute it here. Okay, so this one shall be kg divided by m cube. Okay, so this one will be cancelled and this one will be moved up here. So negative 1 plus 3 is actually 2. So this is m squared s2 squared. So this is how we find for the SI unit for this velocity of the longitudinal waves. Okay, so in terms of dimension, so this one shall be in terms of brackets. So the dimension for the velocity of the longitudinal wave is actually equals to L square st2 square. Oops. This one shall not be brackets. Okay. So this is half. So this one will be L. Oops, this one should be T, which is for the time, dimension of time. So this one is okay, negative here. So this one shall be Lt to the power of -1. So which is same as the velocity, the dimension of velocity. So we can conclude that so this formula is actually dimensionally correct. Okay, so this is the answer for number 1A. So let's move on to part B. Okay, so this is our B. Sketch a graph for a tensile force against the extension of copper wire until it breaks. Okay, so from the previous video, we will discuss about the graph, which is extension against force, but now the question now is asked for the tensile force against extension. So this one, the y-axis should be the force. So the x-axis supposed to be extension. So this is the extension. Okay, so the graph. So the graph we learned from the previous video is actually for the copper. And this one is E and this one is F. Is, if I'm not mistaken, the graph shall be like this for copper. So what if for the force against extension? So this one, so this graph, so as for the inverse for this two graph, so this is the inverse of this graph. So let me slowly draw it. So okay, so this one shall be higher. Yes, this one should be our answer. And so this is the proportional limits and this is the elastic limits until it breaks. Okay, so the yield point, so the question asks for mark the yield point. So the yield point is actually the elastic limits, which is the maximum stress for the object to return to its original shape, as we discussed from the previous video. Okay, so this shall be our yield point. So this is how we draw for the graph of copper, the force against extension for the copper. Okay, so this is part B, and let's move on to part C. So a uniform wire. Okay, let me erase this one first. Okay, let me erase it all. Okay, so let's move on to part C. A uniform wire with the original length, which is L0, 2.40 meter, is connected to two fixed points, and this one should be fixed point. So A and B at horizontal distance of 2.40 meter apart as shown in the figure. So between A and B there are 2.40 meter, and okay, so a mass of 2.0 kg is hung at the midpoint C of the wire. So this is the C. The equilibrium position of C is 0. Okay, so let me, how does this one be 0.27? Okay, so this one shall be 0. Okay, so this one is a mistakes. Okay, so this one shall be 0.27 meter. Okay, so this is 0.27 meter below the level AB. Neglect the weight of the wire and take the Young modulus for its material as, okay, so our Young modulus given here is actually 2.0 times 10 to the power of 11 Newton per meter square. Okay, so calculate the strain of the wire. So how can we calculate the strain for our wire? Okay, so let's see. Okay, so we know that the original length is actually 2.40 meter. So we need to know what is the actual length for AC and BC. So let's take this part as our calculation. So for the half of the original length, so the half of original length is actually 1.20 meter, okay, which is the half of L naught. Okay, so this one is, so this from the level AB to point C is actually 0.27. So basically we are able to find AC by using the Pythagoras theorem, which is 1.20 square plus 0.27 square. So this one is 0.20 square plus 0.27 square. So this is actually 1.23 meters. So AC plus BC is actually 1.23 times 2. 23 times 2. So this is the actual length after the wire has been stretched. So from this information, okay, so this is the length after the wire has been stretched. So from this length and this original length, we are able to find the extension by subtracting between L1 subtract L0. So this one shall be 2.46 minus 2.40. So our extension, so this is extension, 2.46 minus 2.0 is actually 0.06 meters. So this is our extension. So the question asks for the strain. So our strain is actually E divided by L0, which is extension 0.06 divided by the 2.40. So this is our final answer, which is 0.025. So without units, so strain has no units, okay, since meter and meter is will be cancel each other. Okay, so this is how we find for part C number 1. So let's move on to part 2. So let me write it down, the final answer here, which is the extension is actually 0.025. Okay, so this, okay, so calculate the stretch of the wire, stress of the wire. Okay, so we have Young modulus is actually equals to the stress over strain. So our Young modulus is actually 2.0 times 10 to the power of 11. So our stress is what we need to find. So our strain is actually 0.026. So finally, our stress will be 2 times 10 to the power of 11 times 0.026. So our stress, what we got is actually 5.20 times 10 to the power of 9, which is Pascal. Okay, so this is part 2. So let's move on to part 3. So this one should be our strain. Oh, I wrongly write this one. This one should be 0.025 and this one shall be our strain. Okay, so this one is 0.025. Okay, let me calculate again. Times 0.025. Okay, so the answer is actually 5.00 without 2. So that's my mistakes. Okay, so let's move on to part 3. So calculate the energy stored in the wire. Okay, so we need to, okay, so where should I write it? Okay, so let me, stress is actually 5 times 10 to the power of 9 Pascal. Okay, so we need, we know that the energy, which is strain energy, is actually equals to the half TE. Okay, so not T, this is F. So the information that is not given is actually F. So we need to know that what is the actual tension of these two wire. So we have to find the tension. Okay, so in terms of vertical component, so this is the vertical component, by saying that 2t sine theta is actually equals to, okay, so 2t sine theta is actually equals to our mg, which is the mass of the object which is hung at the end of the string, mg. So t is what we need to find. So sine theta is actually, okay, so this, let me redraw again. So this is half of the string, so this is 1.2 meter, and this one is 0.27 meter. Okay, so this is the angle that we need to find. So we can find out that is actually, okay, so tangent, so okay, tangent theta is actually TO, opposite over adjacent. So our angle is actually equals to 1.20, 12.668 degree. So 12.68 degree is actually equals to our mg. So this is the mass of this is actually 2 times 9.81. So the tension is actually equals to 9.81 divided by 2 sine 12.68. So the tension for one side of the string is actually equals to 44.69 newtons. Okay, so let's continue for our strain energy. So strain energy, so since we have both sides, which is AC and BC, so we need to total it up by saying that the strain energy must be times 2 multiplied by 2, which is TE. So it's actually equals to TE. So T is actually 44.69 times the extension. So what will be our extension here? Okay, so what is the extension? Let me find it out. Okay. Oh, I just erased just now. Wait. Okay, strain is actually L naught E over L naught. So E is strain times L naught. So strain is 0.025 times the original length, 2.40. So 0.025 times 2.40, so 0.06 as we got from the previous parts. Okay, so 0.06 meters. So 44.69 times 0.06. So the final answer we got is actually 2.68 joule. Okay, so 2.68 joule. Okay. Wait, there's a mistake here. So let me check again. Okay, so let me recheck again. Okay. Oh, wait. Okay, I'm wondering where was my mistakes. I think my answer is correct. Okay, so this 2.68 is actually for this both tension. So while for one side of the tension, so this strain energies shall divided by 2. So as for one side, which is AC or BC, so 2.68 divided by 2 is actually 1.34 joule. So this is the answer that indicates on the books. Okay, so this is how we find the answer. Okay, so we have done for number 1. Okay, so let us move on to number 2. Okay, let me erase this one. Oops, sorry. Let me erase this one. Okay, so let's move on to number 2. So what happened to this? Okay, so okay, here. Alright, so number 2. A copper wire and fiberglass of the same dimension are each suspended from retort stand. Each of them is then slowly stretched by adding loads to their free ends until they break. Okay, on the same axis, sketch graph of stress against strain to show two materials. Okay, so as for the graph of stress against strain, from the question, from the previous question, the question asked for the force extension. So this one should be the stress and strain. So I'm wondering how I think I should remember for the stress strain graph for copper, which is like this. So let me check for a while. Okay, yeah, this shall be the copper. Okay, so this is the copper. So the copper will undergo the deformation before breaking. Okay, so the copper has the property which is ductile. Okay, so as for the glass is the brittle property, so it will not undergo the deformation. Okay, so it is just a straight line. So this is the graph for two materials. Okay, so this is A. So let's move on to number 2. On the same, okay, no. From your graph, state 3 different characteristics of the materials. Okay, so this is glass. So the question asks for 3 different characteristics. Okay, so as I mentioned just now, which is copper is ductile, while TILE, while glass is actually brittle. So this is the first characteristics between them. Okay, so let's move on to the second characteristics. So as we can see that the stress for copper is higher than expected than the glass. So we can say that copper is actually has the higher tensile strength than glass. So this tensile strength is actually meant by the stress. So stress is tensile strength, and tensile strength is actually stress. Okay, so let's move on to the third properties. So So as we can see that, as we compare for the stress, and let us compare for the strain. So let us see the graph. Let us observe the graph. As we can see that the copper has the higher strain before its break, while um, the glass break at the end of its proportional limits. So we can say that copper is actually is not is okay. Copper actually breaks at higher strain. Higher strain. By saying that copper can be extended until very long before it breaks, while the glass um, breaks until end of its proportional limits. So this is for the part 2. Okay, so let us move on to B. So okay, so this is still number 2, and this is the part B. So a copper wire with initial length of 0.755 meters. Okay, and cross-sectional area of 3.75 times 10 to the power of negative 7 meters square is stretched until the strain is 0.015. Okay, the Young modulus of copper given here is actually 1.30 times 10 to the power of 11 Pascal. So calculate the force applied. Okay, so we have to calculate the force applied. Okay, we know that the Young modulus so have to note that actually the Young modulus has no its own symbol unless the question given by the question, which is E or Y. But if the question is not given but if the symbol is not given in this question, so this symbol is not applicable. Okay, so let's just write it as the Young modulus in terms of full name. So the Young modulus is actually equals to the stress over strain. So stress over strain, we know that is actually Fa times the L naught E. So we need to find what is the force applied. So the Young modulus here given is actually 1.30 times 10 to the power of 11. So force is the one we need to find. So 3.75 times 10 to the power of negative 7. So the original length is actually 0.755 divided by the strain is actually 0.015. So the extension is actually equals to 0.755 times the strain. So this one can be cancelled to each other. So we are able to find our force. 75 times 10 to the power of negative 7 times 0.015. Okay, so the final answer we get is actually 371.3 newtons. Okay, so this is the first part for B. Okay, so for the second part, calculate the strain energy in the wire. So the strain energy basically we know that strain energy is actually equals to half Fe. So the force applied 731.3 times the extension. So the extension is actually 0.755, which is the original length times the strain, which is 0.015. So half 731.3, 0.755 times 0.015. So the final answer we get is actually 4.141 joule. So this is the second part for the question. Okay, so we have done for the second question, so let's move on to the third questions. So let me erase this one. Okay, so let me drag it down a bit. Okay, so I hope you can see clearly. Oops. Okay, so this is number 3. So a wire with a cross-sectional area which is A and unstretched length which is L, original length, so is extended by a force which is F. If the extension of the wire is E extension and the Young modulus of the wire is capital letter E. Okay, so derive an expression for the strain energy stored in the wire. Okay, strain energy, we know that strain energy is actually 0 to E, as we discussed from the previous video. So this is the, okay, so let me explain it again. Okay, let's say I have my force here, so this is my extension. So this is one of example of the material. So this is the proportional limits, which is the triangle. Okay, 0 to E. Okay, so this is our F. Okay, so this strain energy is only only calculated in this region, which is before the elastic limit or before the proportional limits. Proportional limit should be more accurate with by saying that the elastic limit is no more, should I say no more, not included in this triangle. Okay, so this F, we know that F is so we know that E is actually stress over strain. Stress over strain, which is F over A L naught over E. So this is E. So let's say I move it until left the F, I derive in terms of F. So I express it in as F. Okay, so this is EA. So this is EAE over L. Okay, L naught. Okay, so this is how this is what we want. Okay, so this E is actually X, which is the one we need to integrate. Okay, so E, okay, 0. So F is actually E A X over the L. So this EA over L naught is actually a constant. So this is what we want to integrate, x dx. So EA L naught is actually half x squared. So this is E and this is 0. And finally, so let me write it here, EA over L naught is actually half E squared. So this 0 is, we know that it's actually equals to 0. So this is the final answer we got. Okay, so this will be our final answer. Or we can say that half EA, so this E we put it here, over L naught and 1 E, and finally what we get is actually, so this EA over L naught, we sub this F back, so this is FE. This is our final answer. Okay, so this is for part A. Okay, so let's move on to part B. Okay, so let's move on to part B. So this is number 3. An aluminum wire is joined end to end with a brass wire of equal length and diameter. The wire are extended by a force which is 7,600 Newton. If the length and the diameter of each wire is, okay, so the original length for both material is 0.25 meter, and the diameter, so if the diameter is 0.75, so the radius is actually equals to, which is the half, okay, so it's equal to 0.375. So centimeter is times 10 to the power of -2 meter. Okay, so calculate the total extension of the combined wire. So the total extension, so this is the wire which is already extended, so this is the point where they attach to each other. So this is the extension E1 and this is the extension E2. So what we need to find is actually equals to E1 plus E2. Okay, so let us move on. Okay, the Young modulus given here for aluminum and brass, so we can say that Young modulus is actually applicable in this question. So Young modulus, okay, so is there any symbol for Young modulus? Okay, no. So let us just write the full name, Young modulus. Okay, so let's just do for the aluminum first. So Young modulus is actually equals to Fa over L naught E. So I denote this as E1. Okay, so the Young modulus for aluminum is actually 6.9 times 10 to the power of 10. So the F is actually 7,600. Okay, let me rewrite again. So this cross-sectional area is actually pi r square. So this is L naught over E, and this is pi, and this is 0.375 times 10 to the power of -2 pi r square. Okay. So our L naught is actually 0.25, and this is what we need to find. Okay, so E1. Okay, E1 is actually equals to pi 0.375 times 10 to the power of -2 bracket square. 0.25 divided by 6.9 times 10 to the power of 10. So our extension for E1 is actually equals to 6.233 times 10 to the power of negative 4 meter. Okay, as for the brass, so let me drag it down. As for the brass, same formula. So Young modulus is actually equals to F A L naught E, and the Young modulus for brass is actually 9.0 times 10 to the power of 10, and this is the Young modulus, and the force is actually 7600 divided by the pi r square, so 0.375 times 10 to the power of negative 2, which they have the same radius or diameter and same length, of course, 0.25, and this is E2. Okay, so our E2 we got is actually equals to pi 0.375 times 10 to the power negative 2 square, 0.25 over 9 times 10 to the power of 10. So our E2 is actually 4.779 times 10 to the power of negative 4 meters. Okay, so our E1 plus E2, 6.233 times 10 to the power of negative 4 plus 4.779 times 10 to the power of negative 4. So 6.233 times 10 to the power of negative 4 before. So the final answer we got is actually 1.103 times 10 to the power of negative 3. So this is the total extension between two materials. Okay, so let me brought it here. Okay, so we come to our last question. So what is the strain energy stored in the combined wires? Okay, so the strain energy, basically we know that is actually equals to the half Fe. So half, so the force applied is actually 7600 newtons. So as for the extension, which is the total extension between E1 and E2, is actually 1.103 times 10 to the power of negative 3. So this is the final answer. So the final answer we get is actually 4.191 joule. Okay, so let me check whether the answer is correct. Okay, so 4.191. Okay, so 1.101 times 10 to the power of negative 3. Oops, wait, there is a difference a bit between the answer. So let me see where's the difference. Okay, so my E2 is a slightly different here. So the final answer for the total extension is actually 1.101. Okay, so why? Okay, let me recalculate again. So pi 0.375 times 10 to the power negative 2 squared. So 0.25 over 9 times 10 to the power of 10. Okay. Oh yes, okay. So what is the final answer I got? So, okay. Oh, I think here should be the problem. Wait, let me recheck again. Okay, so 6.233 for E1 and 4.779 for E2. Okay. Oops. Okay, so let me find out the total extension again. Plus 4.779 times 10 to the power negative 4. Oh yes, the answer should be 1.101. Yes. Okay, so this should be correct. Okay, so there's a mistake here. Okay, 1.101. Okay, so the final answer we get for the strain energy is actually equals to 101 times 10 to the power of negative 3. Okay, so the answer is actually 4.184. Okay, so this is the final answers. Alright, we have done for the 3 questions. So this is how we answer the question step by steps. Okay, so I hope you can understand after watching this video. Okay, so I think we stop here and I'll see you in the next video. So if there's any question need to be asked, please comment in this below this video. Okay, so I'll see you next time. Okay, bye.